To see where these graphs come from, we are going to look at a little bit of calculus. So it's not needed for everyone, but if you're interested, you can look at these videos. So we are looking at zero order, meaning that A is a reactant that is being consumed to give you product, but the rate is independent of its concentration. So rate for this reaction is K times A, concentration of A to power 0. Now this is also equal to a change in concentration of A over a change in concentration of T. In order to be able to integrate, we are going to make this change extremely small, and instead of delta we put D as if it's a derivative, and then we take its integral. Now a few things we should sort of agree so we can use it and then get used to it. When time is equal to 0, we say concentration of A is equal to A0. So it's an initial concentration. When time is equal to T, when you stop the reaction, we say concentration of A is simply equal to A. So if those limits are okay, let's just see what happens when we take the integral. So for this reaction, we're saying minus dA over dt is simply equal to K because it was multiplied by A to power 0, so it became K. Now we are going to take it to a different side of equation. So this is K dt. I'm going to put the minus on the other side, meaning I multiply both sides by -1, minus K dt. Now what we can do is, like, this is dx, or this is dx, this is dy. We are going to take its integral, and we go from a0 to a as our limit, and we take integral of time, and we go from 0 to time t. Integral of dx is just x, so you should agree with that. So this becomes, after integration, is a with limits of a0 to a. On the other side, you have minus k times t with limits of 0 to time t. So what we have is a minus a0 is equal to minus kt. So now I take a and keep it as my left-hand side of equation, and take minus a to other side, minus kt plus a0. So this is the final integrated version of it. And if you look at it carefully, it looks like an equation of straight line. This is your y, and this is your mx, and this is your intercept b. So intercept here is, this is your a0. For example, you have 8 particles, and it's being consumed, and your slope is minus k, so this is the slope here. And when you stop time, and that's where you have a, this equation goes linearly to 0. Here you will have 1 particle, then you have none. So this is integration of 0 order. Let's look at first order. Same concept applies, but this time we have rate equals to minus dA over dt. Since it's first order, it's equal to k times a to power 1. So I'm going to do the same thing. I take a to left-hand side, so I have derivative of a over a is like 1 over x dx. I will take this integral, go from a0 to a. On the other side, I have minus k dt, and I'm going to go from 0 to limit of time. When we do 1 over x dx is natural log of x, so in this case it's natural log of a0 to a is equal to minus kt from time 0 to time t. And when we do that, we have natural log of a minus natural log of a0 is equal to minus kt. Now save natural log of A as your y left hand side. Take the other one the other side, minus kt plus natural log of A0. So it's a e factor or exponential factor. That's how the decay works, and this time your y is this. So if you want to have a straight line, this is how you should look at it. This is natural log of, I took one example which is first order, I'm sure of that, that's why I took. This is declining, and the slope here is minus k, because this is your mx, and this is your intercept. Here you have natural log of a0 when n205 had a number to begin with, and it's being declined. Now look, if you look at this is exponential decay, e decay, and if you have 8 particles here, after a while, your first half-life, this is when t half, you have 4, then you have 2, it never reaches 0, so it's being decayed constantly, gets smaller, but never goes to 0. So that's why the graph looks like this versus a straight line. Now finally, let's look at the second order for sake of IB. So this is second order when rate is equal to k times A reactant squared, and it's equal to minus dA over dt. So keep dt on the right hand side, bring and keep dA over A squared on the left hand side. Take integral of this side, go from A0 to A, and then on the other side you have minus k dt as before, go from 0 to time t. Now this is 1 over x squared, or x minus 2, when you take its integral is minus 1 over a, with limits of a0 to a, and the other side you have minus k t from 0 to t. So here you have minus 1 over a, minus and minus becomes positive, 1 over a0 is equal to minus kt. So what we can say is minus 1 over a is equal to minus kt minus 1 over a0. Multiply both sides by 1, minus 1, so everything becomes positive. 1 over a this time. This is how the graph looks like. If you have 1 over a is equal to positive kt plus 1 over a0. So the slope this time is k, because this is mx this time plus b, and this is your y. So the intercept here is 1 over a0. Now this is why your graph of a versus time for second order looks like this. They get closer to x-axis and y-axis as you are being consumed, and your half-lives are constantly getting bigger. So if some of you were interested to know where the graphs of concentration coming from and why they are different, it's because of a little bit of calculus that is involved.